Hey everyone, it's Mr. Moore, your science teacher. So today we're just going to go over weight and mass, and we're going to do this gizmo together. So this is what the gizmo looks like, and then the questions are going to be in here. So I'm just going to put my name, Mr. Moore. Okay. We're going to put our date at the top. Today's date, 10/10/23. Okay, so student exploration, weight and mass. Vocabulary that you're going to see in this exercise is going to be balance, force, gravity, mass, Newton, spring scale, and weight. Prior knowledge questions, do these before using the gizmo. Your weight is the pull of gravity on your body. Suppose you step on a bathroom scale on the moon. How would your weight on the moon compare to your weight on Earth? So because there's less gravity on the moon, your weight is going to be impacted by the gravity. So gravity on the Earth is 9.8 meters per second squared. Gravity on the moon, I believe, is 1.6 meters per second square or less than that. So your weight is going to be less on the moon. So I underlined your answer right here. Actually, maybe I'll highlight that. Okay, so your answer is going to be B. It's going to be less on the moon. So question 2 is going to ask your mass is the amount of matter or stuff in your body. How would your mass on the moon compare to your mass on the Earth? So mass stays the same regardless of whether you're on the Earth, whether you're on the moon, Jupiter, or some other location. Your mass remains the same because it's the amount of matter that your body makes up. So your mass would be same on the Earth as on the moon. So that's going to be C. So on the weight and mass gizmo, you can use a balance to compare the masses of objects. So a balance is like a scale that lets you, like it says, balance weight between two objects. So place the dog on the right pan of the balance. What happens? So put the dog on the right. So the dog causes the balance to go down. So you would say balance goes down. Okay. Place a 5 kilogram mass on the other pan. Which has more mass, the dog or the 5 kilogram mass? So this is 5 kilograms right here. So you put that up there and boom. So the 5 kilogram mass is heavier than the dog. So you put 5 kilogram mass as your answer. Number 3, the 5 kilogram, 5,000 gram mass is heavier than the dog. So take it off the pan and place a 1 kilogram, 1,000 gram mass on the pan. Add 1 kilogram masses to the left pan until it goes down. Then take one of the 1 kilogram masses off the pan so that the masses are above the dog. Use this process of adding and subtracting other masses from the left pan until the two pans are balanced. Add up all the masses on the left pan. This is equal to the mass of the dog. And then it says, what is the mass of the dog? So let's go back. Okay, so we'll take the 5,000 off. 1,000 kilograms, 2,000 kilograms, 3,000 kilograms. Okay, so that's too heavy. This is too light. So we're getting closer. So we got 2,000. Let's say, okay, so we put the 500 grams. It's still too heavy. So 2,100 grams, 2,200 grams, 2,300 grams, 2,400 grams. Okay, so 2,400 grams is too heavy. So we're getting even closer. So 2,350. Okay, a little bit closer. 2,360, a little bit closer. And then 2,370. That's exactly right. So the dog weighs we're going to say 2,370 grams. Or 2.37 kilograms. Because remember, 1,000 grams equals 1 kilogram. So 2,300. Oh, I said 79. I meant to say 70 or 2.37 kilograms. Okay. Get the gizmo ready. So activity A, weight on different planets. Click clear scales to remove all objects from the spring scale and the balance. Click the center of the crossbeam of the balance to turn off the mass display. A spring scale is used to measure force. Since weight is a type of force, a spring scale can measure weight. The metric unit of force is called the Newton, or an N for short. Will an object's weight change on different planets? Measure. Place the pumpkin on the spring scale. Click the red line on the scale to see the weight measured to the nearest Newton. What is the weight of the pumpkin? Okay, so we'll go back to the pumpkin. We're going to clear scales. And this is the spring scale right here. So right now you can see it's at 0 newtons. And when we add a pumpkin to it, and then we go down, so it looks like 25, but so it says 30 newtons. So 30 newtons is going to be your answer for this question. Predict. If you take an object to a different planet, do you think its weight will stay the same or be different? So mass stays the same, but weight always changes depending on the gravity. So it's going to be different. Collect data. Measure the weights of the following objects on Earth, the Moon, Mars, and Jupiter. Record your measurements in the data table below. Okay, so we're going to do pumpkin, weight on Earth, weight on the Moon, weight on Mars, and weight on Jupiter. So we're going to do, okay, so we know, and this is in newtons. So we already know pumpkin is 30 newtons on the Earth. Now we're going to do, now we're going to change it right here. Moon, 5 newtons. Mars, 11.4 newtons. Jupiter, 75.9 newtons. So we have 5 newtons, 11.4 newtons, and 79.1 newtons. I might be wrong. Let me go back and check. 75.9, 11.4. Okay. So 79.5 or 75.9, excuse me, 9 newtons. Okay. And then we're going to do the dog. Okay. And clear the scales. Back to Earth. The dog is 23.2 newtons. So you put 23.2 newtons. And then Moon, 3.8 newtons. Okay. And then Mars, 8.8 newtons. And then Jupiter, 58.8 newtons. Okay. We're going to go to the watermelon. So we're going to clear the scales. We're going to go back to Earth. We're going to put the watermelon on there. 96.5 newtons. Oops, excuse me. Then we're going to do Moon, 16 newtons. Mars, 36.5 newtons. And Jupiter. It's going to be 244.2 newtons. It's pretty big, actually. Okay, so does the weight of an object change when it is moved to a different planet? So your answer would be a resounding yes. Extend your thinking. Which celestial body has the strongest gravity? Earth, the moon, Mars, or Jupiter? Explain how you know. So celestial body just means in the stars or in space. So the strongest gravity, so we would look at this. So weight of the pumpkin weighs the most on Jupiter. The weight of the dog also weighs the most on Jupiter. The watermelon weighs the most, 244.2 newtons on Jupiter. So we would say Jupiter has the greatest gravity because all the objects weigh more on Jupiter. Okay. So moving right along. Activity B, mass on different planets. Click clear scales. Introduction, define mass using the balance. Place the object on the right pan of the balance and then add and subtract masses until the pans are even. Add up the masses and write each mass in grams. Remember, there are 1,000 grams in 1 kilogram, so the 1 kilogram mass equals 1,000 grams. How do weight and mass change on different planets? If you take an object to a different planet, do you think its mass will stay the same or be different? So remember, weight changes on a planet, but mass stays the same. Okay? So we're going to collect data, use the balance to measure the masses of the following objects on Earth, the Moon, Mars, and Jupiter. Record your measurements in the data table below. Okay, so we're going to do the pumpkin. So we're going to clear scales. Go here. Earth. Remember, we're measuring in kilograms, so that's too much. 1,000 grams, 2,000 grams, 3,000 grams. Okay, so 4,000 grams is too much, so 35, okay, that's still too much. 3,000, still too much, okay. 3,050 grams. 3,060 grams. Seems about right. And then what did the directions say? Okay, so it would be okay, so we're going to clear scales. We're going to try that one more time. So we're going to do, oh, sorry. We're going to do the pumpkin. I'm going to do 1, 2,000, 3,000. We're going to do 50. Okay. Okay, so it should be 3,060. So the mass of the pumpkin on Earth is 3,060. Or I guess it would be 3.06 kilograms, but just stick with the grams for now. So you're going to do that for each of these objects. You're going to do for the pumpkin, you're going to do it for the dog, you're going to do it for the watermelon. And you're going to add up each of the weights to see what the mass of the object is. But we're going to move on for now. So does the mass of an object change when it is moved to a different planet? Oh, actually. So here, the moon, Mars, Jupiter. So does the mass change? No. Okay. So we know that the mass of the pumpkin is the same on every planet. So you just copy, and paste. Okay, so then you're going to do the dog and the watermelon by yourself. Does the mass of an object change when it moves to a different planet? And you would say no. The mass stays the same. Draw conclusions. Based on what you have learned about mass and weight, why do you think the mass did not change, but the weight did? So you're going to come up with your own answer, but my estimation would be mass stays the same regardless of gravitational forces. Weight is changed by less or more gravity. So the more gravity on a planet, the heavier an object will be. The less gravity on a planet, the lighter it will be. So extend your thinking. First, using the balance, find the mass of a pumpkin on Jupiter. Then place the pumpkin on the spring scale and record its weight. Finally, remove the pumpkin and weigh the masses from the balance on the spring scale. How do the weights compare? Okay, that's easy. So, mass of a pumpkin on Jupiter. Okay, so that makes sense. Okay, so we're going to clear scales. So we're going to weigh the pumpkin. Okay, so it's going to be boom, boom, boom. Okay. Okay, so we know the pumpkin on the spring scale is 3,060 grams. Okay, so that is the weight of the pumpkin on the balance. So on the spring scale, what is it going to be? And your answer is going to be in newtons, right? So we're going to clear scales. Okay. So it's going to be 75.9 newtons. So it's going to be 75.9 newtons, right? Now, how about the weights? Weights on spring scale. So we're going to go back, clear scales, okay? So we're going to weigh the pumpkin. So it's going to be boom, boom. So 3,000, 3,050, 3,060, okay? And then what does it say? It says to put the weights on the spring scale. And then we're going to measure what's the newtons. So it's also 75.9 newtons. Weights on spring scale, 75.9 newtons. So because the mass of the weights and the pumpkin are the same when you measure them on the spring scale, the newtons are the same. Okay? Okay, in this last sheet, how strong is gravity on Mars, Jupiter, and the Moon? Using the spring scale, measure the weights of objects on different planets. List the 3 planets and the Moon from strongest gravity to weakest. Okay. So we would go to Earth. So pumpkin. Pumpkin on Earth, 96.5 newtons. On the Moon, 16 newtons. On Mars, 36.5 newtons. On Jupiter, 244.2 newtons. So we know that strongest is gravity from strongest to weakest is Jupiter. After that is the Earth, the Mars, and finally the Moon. On which planet or moon do you think the 5 kilogram mass will weigh the most or the least? So I predict that most will be on Jupiter. Correctly. And then least on the moon. So let's put that prediction to the test. Okay, so it's saying 5 kilogram mass. So in Jupiter, it's 123 newtons, 0.9 newtons. Mars, it's 18.6. The moon, it's 8.1. And on Earth, it's 49 newtons. So we are correct. The moon was the least, and Jupiter was the greatest. Find the weight of the 5 kilogram mass at each location. Okay. So on Earth, it's 49 newtons. So we're going to put 49 newtons. On the moon, it's 8.1 newtons. On Mars, it's 18.6 newtons. And on Jupiter, it's 123.9 newtons. 123.9 newtons. Okay, was your prediction correct? Find the weight. So yes, I predicted that Jupiter would have the greatest mass, or find the weight. Jupiter would have the greatest weight, and the moon would have the least weight. Calculate. Weight depends on mass and the strength of gravity. Estimate the strength of gravity on each location by dividing the weight of 5 kilogram mass by 5. Okay. So flower pot mass, kilograms or grams. Predicted flower pot weight, newtons. Okay. So mass and strength of gravity. Estimate the strength of gravity on each location by dividing the weight of 5 kilograms. 5 kilogram mass by 5. Okay. So you're going to go to your calculator. Okay, so for this first one, you're going to do 49 divided by 5. It's going to be 9.8. Okay. Okay, and then you're going to do 8.1 divided by 5. It's going to give you 1.62. You go to Mars, you're going to do clear 18.6 divided by 5, 3.72. And finally, Jupiter, going to do 123.9 divided by 5. It's going to give you 24.78. Okay. Calculate. First, measure the mass of the flower pot in the gizmo. Then predict the weight of the flower pot on each planet. Multiply the mass by that planet's strength of gravity. Finally, check your predictions by actually weighing the flower pot on each planet using the gizmo. Okay. Okay, so the mass of the flower pot. Okay. So the mass is going to be the same regardless of where we are. So flower pot. Okay, that's too heavy. So 1,000 grams, 2,000 grams, 3,000 grams, 4,000 grams. 4,500 is too much. 4,100, 4,200, 4,300. Okay, 4,300 is too much. 4,250, 4,260, 4,270. Okay, so it's going to be 4,270 grams. And that mass is going to be the same no matter what planet it's on. Predicted flower pot weight. Okay. So I'm going to make up some numbers here. I'm going to say 18 newtons on Earth. This is just me guessing. It's very inaccurate. 14.3 newtons, and let's say 47 newtons. This is just a guess. And then we're going to go and we're going to calculate it. So 41.8 newtons on the Earth. On the Moon, 6.9. On Mars, 15.8. And on Jupiter, 105.9. Okay, so I was slightly off, but I was mostly just making my predictions. So that's the point of science. You're supposed to make predictions and then do the actual tests and the actual measurements and find out what the real answer is. So thank you for watching. I hope this helped, and I will see you in the next lesson. Bye.